Alright, so today's pre-lecture video, we're starting chapter 22, which deals with Gauss's law. And I've chosen to sort of talk about the application of Gauss's law in this video. It might be a little bit near the end of what we may cover in Thursday's class, but I think that, again, it is an example of something that it is good for you to see several times. So I don't think the repetition will end up hurting when we do get to cover it in class. So when we talk about Gauss's law, we're talking about the net electric flux through a surface. So in your reading, you learned that the definition of electric flux can be written like this. So this represents flux. And it's the passage of an electric field through a surface area. We can calculate it with a simple dot product of electric field and area if the electric field is constant. But the more general way is to do the integration, which will allow for the possibility that the electric field may be changing in magnitude or changing its orientation relative to the area. This symbol right here means that we're doing the integral around a closed surface. And what we eventually find when we do Gauss's law is we find that if you do the integration around a closed surface, it is equal to the charge that's enclosed in the surface over the epsilon naught. That was that symbol that we ran into the other day that they were using to express electric field. So the perk of this Gauss's law is it's going to allow us to calculate the electric field a lot more easily than how we looked at it at the end of chapter 21, where we were doing the integration with dq's and how is the electric field pointing and what's going to be the net direction. This ends up being a lot easier. So we do have to be careful. Now, Gauss's law can't be used to find the electric field all the time. There are going to be certain cases where it works. And these rules will help you sort of see, is this a case where it's going to work. So basically, the first thing is you're going to choose a surface that mimics the shape of the charge distribution. And it is going to be true that Gauss's law is only going to work for charge distributions that are relatively simple or uniform or symmetric, things like that. And we'll look at two examples at the end of this video. When you choose your surface that's mimicking your charge distribution, you also want to choose the surface so that at the surface that you have, the electric field should either be parallel to the surface or perpendicular to the surface. If it's perpendicular to the actual surface, then you get the greatest contribution. If it's parallel to the surface, remember that means then you won't have any flux and that won't contribute at all. It's also nice if you want to choose a surface where the electric field is constant, so then that allows it to come outside of the integral, and then you can actually calculate for the electric field. So if you sort of keep these things in mind, the calculation becomes a lot easier. So the first example that we're going to do is we're going to talk about an insulating sphere of charge. Now, if you remember, when you have an insulator, the charge is going to be spread all the way through it, like all through it, and the charges don't really move. So let's say that this sphere has a total charge Q, and we're going to say it has a radius of big R. All right? So we know, because it has a positive charge, that if we drew the electric field lines, they would be passing out radially from the charge. Sort of like this. So thinking of the rules or the way that we talked about it, we want to choose a surface that sort of mimics this charge distribution, and also one where the electric field would be constant on the surface, and either parallel or perpendicular to the surface. Well, if I want to mimic the surface, it seems to me that enclosing this sphere of charge with another sphere would make a lot of sense. And just to be clear, right now we're finding the electric field for some r which is greater than the radius of the actual charge distribution. So we start with Gauss's law, E dot dA equals the Q inside or enclosed over epsilon naught. Now, if these are the red lines are the electric field lines, the area vectors, or the dA, would look like this. Notice they're parallel to each other. And so what that means is that I can just write this as just E dA. The dot can disappear because it's the same as E dA times the cosine of the angle between them. And in this case, the cosine of the angle, well, the angle's 0, and the cosine was B1. Qn over epsilon naught. I'm going to do one side at a time. Now, because the electric field is constant, I can take it outside of the integral. And if I integrate over the entire area, dA, that's going to give me just A. Now I'm going to do something about the right-hand side. How much charge have I enclosed? I've enclosed the entire charge of the insulating sphere, which is big Q. Now, can I write the area a different way? Well, the surface area of the sphere that enclosed my charge distribution has an area of 4 pi r squared. Those are things we need to remember. And now I'm finally able to rearrange this and find the electric field. And notice that my expression looks just like that of a point charge. And that's kind of an interesting result, is that the electric field outside of this solid sphere that has, a size to it, it's not a point charge, but when I'm outside of the surface of that charge distribution, it ends up creating an electric field that looks just like a point charge. Now, what I didn't do is I didn't look at the case where, what if I'm inside the sphere? So we still have a total charge of Q. But what if I wanted to look at somewhere where this is the radius, but this is my R, for R is smaller than the radius of the sphere. Now, I'm still going to find that the electric field lines are going to come out radially. And so a lot of things about my calculation are going to be really similar. I've chosen my surface so that the electric field lines and the area vector are parallel to each other. So this just becomes EdA. The electric field is constant on my surface, so it comes outside of the integral. When I integrate over dA over the entire surface, I get the area. And the area is 4 pi r squared. But what is the charge that I've enclosed? Well, it's a uniform charge distribution, so it basically means that the charge per unit volume is a constant. It means that no matter what size piece I take of the sphere, I'm going to get a proportional amount of charge. So I can make a ratio. If I take the entire radius, if I take the entire sphere, I get a total charge of Q, and the volume is 4 pi r cubed. But if I take a smaller piece, which has the smaller radius, I'm only going to get that q in. So I can rearrange this, and q in is going to be a fraction of the total charge. The way this is going to work is it's going to be 4/3 pi little r cubed over 4/3 pi big R cubed times q. So it's just little r cubed over big R cubed q. So I'm going to go back and I'm going to put this right here. So I get E times 4 pi little r squared is equal to r cubed over big R cubed times q. And so over epsilon naught. And if I solve for E, I get 1 over 4 pi epsilon naught r cubed over r squared q over big R cubed. And finally, and so what's going to happen is I'm going to get a fraction of the total charge. And look, when little r is equal to big R, then the electric field will end up looking just like the point charge again. So what happens is, if we looked at a graph of the electric field for the sphere, and this is big R, what's going to happen is the electric field is going to increase linearly with R, and then when I get to the surface, where it's going to have 1 over 4 pi epsilon naught big Q over R squared will be that value, and then it's going to start to drop off as 1 over little r squared. And so it sort of decreases like that. And that's what the insulating sphere looks like. Really quickly, we're going to do a line of charge, one that's really long. We'll make it positive. And so we're going to just say that it has a uniform charge per unit length. And if we imagine the electric field is coming out in all directions, it might make more sense if I do a top view. And if we look at it from the top, the electric field would be coming out like this. And so what our Gaussian surface we end up choosing to mimic the charge distribution is a cylinder, because at the sides the electric field is going to be parallel to the area, but at the tops and the bottoms the electric field is going to be perpendicular to the area vector. And to understand that, just remind yourself how the area vector is being calculated. So when I do E dot dA equals Q in over epsilon naught, this breaks into the electric field at the sides of the cylinder plus the electric field, electric flux, in the top and bottom. At the top and bottom, there is no flux, so that doesn't contribute. And at the sides, along the side, the electric field is parallel to the area, so you get E dA, And the electric field is also constant over that surface, dA. Now, let's just say that the length of our cylinder, or the height, is L. And so the area is going to be 2 pi, oh, I forgot to say this is going to be the distance r, 2 pi r times L, and that's equal to the charge that I've enclosed over epsilon naught. Now, how much charge do I get in this cylinder? Well, again, lambda is the total charge over the total length. Q in over L allows us to solve for this, and Q in is going to be lambda times L. And so we have E times 2 pi r L equals lambda L over epsilon naught. My electric field is equal to lambda L over 2 pi epsilon naught over RL. And so this ends up to be lambda over 2 pi epsilon naught R. And I don't know if you remember it, but this was a result they looked at when we did the segment of charge in the previous chapter. They also looked, well, what if the line of charge is very, very long? And this is the result that we would get. And those are our examples of using Gauss's law to find the electric field.